All right. So hi, Leonard.
Hi, Yang.
Yes. The other speaker is also here, or you guys will?
Yes. So Hami is just signing up now to be able to join the.
Okay. Okay. We can wait a sec. Yeah.
I can start sharing my screen.
Yes, please.
Can you see the slides?
Yes, we can. We can. Yes.
Okay. Awesome. Oh, I think
All
Soham
right.
is in
So
now.
here. Yes. Okay. Oh, right. So then let's get started. So thanks for everyone for taking the time to join the seminar, Privacy and Security Machine Learning Seminars. And today we are very happy and honored to have two research scientists from DeepMind to actually give us a talk on differential privacy and image classification. So we have two speakers today. So Soham and Leonard. So they are both research scientists at DeepMind, and they actually both work on optimization, and they obtained their PhD from University of Maryland and well as University of Oxford. So of course, due to some Emiliano's family issues, so he cannot chair the session, so we started the seminar a little bit late. But anyway, so without further ado, so the floor is yours. Please go ahead.
Thank you very much for inviting us. Very happy to be presenting this work, Unlocking High Accuracy Differentially Private Image Classification through Scale. So this is a joint work with Soham here in the call, who's joint first author, and our other collaborators in DeepMind, Jamie, Sam, and Borja. We're giving here the link to the paper which is available on arXiv, and the code is open sourced on GitHub. Okay, so the motivation for our work is that machine learning models can leak training data, and people attending this seminar might be very familiar with this XKCD, where the idea is that when we train on sensitive data, if we don't take any particular care about how we train our model, then it might, when using this model, it might reveal sensitive information. And this is something that has been shown in the literature for language models, for instance, with this work from Carney et al., where they showed that they could extract sensitive information from GPT-2. And perhaps more surprisingly, even from image classifiers, it's possible to reconstruct images of the training set from an image classifier, and this is work that Borja, Jamie, and collaborator have been recently showing. And so based on this observation, our goal is to train models that do not present this privacy issue. And for that, we look at the framework of differential privacy. And what we want is to be able to train models with differential privacy while maintaining a high accuracy of the model that we train. So this is a summary of our main results of this work. And so on the left hand side, we have the SOTA on CIFAR10 over time. And on the right-hand side, we have results on ImageNet and the SOTA on private training as well. And so if we start with CIFAR10, what we see is that the evolution of the SOTA over time has not been increasing very fast, and only reaching a little bit under 72% earlier this year in 2022 before our work was published. And when we look at ImageNet, we can see that the private SOTA is at epsilon 8 is still very far away from the non-private SOTA, which is at around 91%. And what we show in this work is that we can really improve the performance of the models that we train with differential privacy. And on CIFAR10, we achieved the largest improvement to date in terms of accuracy. And on ImageNet, we also have a considerable boost of performance. And this level of performance allows us to start talking about practically useful levels of accuracy on ImageNet. This is larger, for instance, than some ResNets, some smaller ResNets trained on ImageNet without any privacy. And so overall, we obtain state-of-the-art results on CIFAR10, ImageNet, and other data sets by quite large margins. So how do we do this? So like we're going to detail in this talk how we get these results. And the outline is as follows. I'm going to start by giving a bit of background on differential privacy and differentially private stochastic gradient descent. And then show how, when using DP-SGD, we can improve the convergence and trainability of deep neural networks so that we can get better performance. And then Soham will talk about leveraging pre-training, and then in the last section, we'll give some intuition about how to tune hyperparameters and how the regime that we're looking at with DP training behaves differently than standard training. So let's get started with the background. So here, this slide is a summary of some property that we get out of training with differential privacy. So what we're looking at in these yellow boxes is an algorithm that is randomized and that we assume to satisfy epsilon DP, so epsilon differential privacy. And then the property that we obtain from this setup is that if we train some models with this algorithm, and so we can train a model on a data set that would include my data, so that's the top left box here, then this doing so induces a distribution over models that we call P. And if we do the same training with the same algorithm, but on the same data set, with the exception that now we have removed my data, then doing so induces another distribution that we call Q. And the guarantee that that differential privacy gives us is that the distance between P and Q, so here quantified by the KL divergence, is in the order of epsilon squared. So what that means is that the distributions are very small when epsilon is small. And so in other words, when we look at the models that are obtained after training with differential privacy, then there is no way of knowing whether my particular data has been used during training or not. And therefore, a fortiori, then that my data is protected because we cannot even tell if it has been used during training. So this is, in a few words, the nice guarantee of differential privacy that we get when training models with algorithms that satisfy this property. So why is DP desirable for training machine learning models? Where there have been a number of organizations and companies that have been using differential privacy in the past few years for some key projects. And the reason for that is that DP has very nice properties. So we are listing a few here. The first one is that it's robust to powerful adversaries, even when these adversaries have unbounded computations and access to arbitrary side knowledge. It also does not rely on obscurity, which means that we can publish our algorithms and how we train, all the details about our training procedures. And then finally, DP gives us a way to quantify the amount of privacy that we're providing. So we have this parameter called epsilon that I have already mentioned that is a privacy budget, and it quantifies how private we are. And just to reiterate, the lower epsilon, the more private our algorithm is. Now, how to choose the particular value of epsilon is something that is really task dependent and is more of a policy question. And it will really depend on the applications and potentially also on utility or accuracy requirements. So here we have a number of examples of the epsilon values that have been used in different projects. And in this paper, we try to explore a range of values to show how utility degrades with epsilon or rather improves when we increase it. And we consider values between 1 and 8, with 8 being considered standard for a few of the image classification benchmarks that we have been looking at. So how do we actually train models with differential privacy? So for that, we use Differentially Private SGD, so Differentially Private Stochastic Gradient Descent. And what DP-SGD does is really performing an update that is very similar in spirit to what SGD does, except that the gradient is privatized before we actually perform the updates to modify the model parameters. So the setting in which DP-SGD is relevant is when we have a trusted party that trains a machine learning model on a private data set. And a property that is worth pointing out here is that because every update uses only privatized gradient, then the model can be released at any point, which is a property that we will exploit later. So looking a little bit more in detail about how any of this DP-SGD looks like. So again, this is really similar to SGD with two main modifications here in blue and red. The first one is that each individual gradient per sample is clipped to a maximum norm of C, a maximum L2 norm of C, which allows us to influence to bound the influence of any particular sample on the gradient. And the second modification in red is that we add some Gaussian noise that is proportional to C, and to sigma, the standard deviation, and to 1/b, the batch size. So it's worth pointing out that we are going to run these updates many times, and every time that we apply this update, then we are going to lose a little bit of privacy. And so overall, the privacy loss epsilon will increase as we repetitively apply these updates. It will also decrease if we add more noise, and it will increase with batch size. And this will, all of these will have impacts on practical performance, as we will see later. So we've seen that the DP-SGD is very similar to standard SGD with a few minor modifications. But these modifications have a very large impact on being able to successfully apply it to train neural networks. And so there are three main challenges that we identify here. Challenges to get good performance when training neural networks with DP-SGD. The first one is that, as we've said before, usually we are given a privacy budget epsilon. And this creates a trade-off between the number of iterations that we can run DP-SGD for and the amount of noise that we apply at each iteration. And what this means is that, for instance, we cannot hope to have the noise wash out because we run our training algorithms for very long, and therefore the noise disappears, because this would not satisfy our constraint on satisfying this privacy budget epsilon. The second aspect of this is that the hyperparameters, like the modifications to this update, creates very different dynamics, and therefore the hyperparameters that have been very carefully chosen by the community before and all the regularization schemes that have been devised typically do not work well out of the box when training with DP-SGD. And so we have to really spend a lot of effort and care about tuning these hyperparameters and choose our regularization in the right way to get good performance. And if we zoom in, to look more closely at the update of DP-SGD, then we can see that the clipping per sample and the noise introduce two difficulties at a low level. The first one is that the privatized gradient is biased, and that's due to the clipping per sample that is going to rescale the influence of each gradient per sample. And the second one is that the privatized gradient has a high variance due to the noise addition. And in our experience, it's really the variance that is the limiting factor in getting good performance, and that we need to pay a lot of attention to. And putting all of this together at a more macro level, this creates a challenge to make standard models work. So the computer vision community has been creating architectures that are very powerful for image classification, for instance. But typically, these models have a large number of parameters, and so they have a large dimension. And this means that the L2 norm of the noise which scales with the model dimension, will be quite large. And so this like hints that it might create some learning difficulties. And the other thing is that some modules, such as batch normalization, which are very common, might not work very well out of the box when we train with DP. So our approach can be summarized in these 3 ways. First, we're going to be using standard deep learning architectures in this work, unlike the community that has been sometimes focusing on more custom architectures. The second is that we are going to be pushing the limits of vanilla DP-SGD without modifying the algorithm, but making sure that we tune our hyperparameters in the right way and use enough compute. And the third one is that we are going to improve trainability and convergence of DP-SGD using tricks of optimization for non-private training of neural networks. And it's worth stating that getting all the details right was really important to get good performance in practice. Okay, so let's look at now methods to improve convergence and trainability of deep neural networks. So what I'm going to show next is an ablation study to understand which components are important to get good performance. And so the setup that we look at is classification for CIFAR10 with the guarantees of epsilon equal to 8 and delta equal to E-5 as our DP hyperparameters. And the model is a wide ResNet of depth 40 and width 4, which will use the acronym WRN40 for in the following slides. And our approach is that we're going to be adding a single ingredient at a time and observe the improvement in performance for each of those. So our baseline that we start with is that we use this model wide ResNet 44, but we remove batch normalization because batch normalization is this module that people in computer vision have been using extensively to be able to normalize the signal within our networks to ensure good signal propagation and good training dynamics. And it's typically placed on the residual branch for deep residual networks. And this is really crucial for good performance in practice. But unfortunately, it doesn't play well with training with DP-SGD because it introduces a dependency between the samples. So this is the baseline that we obtained by just taking the standard architecture of wide ResNet 44, and we just remove batch normalization since that doesn't work well with DP. And the validation accuracy that we obtain is around 51%. So the first modification that we do is that we use this literature, this work that have been focusing on removing batch normalization in non-private training and replacing it with other methods, such as other normalization techniques, or introducing a rescaling factor on the residual branch, so as to achieve the same effect as batch normalization, but without introducing this dependency between samples. So here we use group normalization, which is another normalization scheme, but normalizer-free methods would also work well here. And it's worth pointing out that it's really crucial to place whether you're using a rescaling factor or another normalization method, it's really crucial to place it on the residual branch of deep residual networks, as we show on the bottom right. And using this normalization scheme gives us a big boost of performance already, taking us to 66% validation accuracy. Now, the second trick that we look at here is increasing the batch size. So there has been other works that have been observing this, and we confirm this effect here that using a large batch size is really useful to get good performance when training with DP-SGD. And in particular, we observe that using a large batch size improves the signal to noise ratio of privatized gradients, and this results in better performance. So here on the bottom right, the plot that we see is the accuracy as a function of the batch size, plotted both for the training set and the validation set. And we observe that in both cases, the accuracy increases significantly as we increase the batch size. And it's worth mentioning that for each of these plots, we are tuning the learning rate and the amount of noise that we get so that each of these points here correspond to a different training run that has been well tuned to really see the effect of the batch size here. Another trick that we use that I'm not going to spend too much time on is weight standardization, which is another trick on top of group normalization that helps give us better signal propagation in our model and get better training dynamics, which gives us an additional 1% improvement. But more importantly is this trick of augmentation multiplicity, which really gives a large improvement in practice, both on training and validation. And so the idea of using augmentation multiplicity is to exploit data augmentation in a particular way. So data augmentation is heavily used in computer vision, in particular in image classification. So you can think of, like, we can see this example here of where we take an image of a fox, and then we can do random horizontal flips or taking random crops of the image, and then the model should still predict the same label based on these different augmentations. And typically what happens in deep learning is that for each image, one augmentation is, one random augmentation is applied to that image, and that changes every time we get a mini batch of data. But here, this augmentation multiplicity, which has been introduced in other papers for non-private training, has shown that it's useful to perform multiple augmentations of the same image within one mini batch. And so, for instance, here, if we do 3 augmentations per image, the mini batch would increase of size by 3-fold. And so, again, just to reiterate, these different images come from the same original image, but they're like going to be processed within the same mini batch by the model as we train on this data. And the nice trick here is that because all of these images come from the same data, we can bundle them together by computing the average gradient over these different augmentations, and then clip them as one unit. And therefore, you really consider them as just coming from the same data and consuming one data point. And so overall, what this gives us is that it reduces the variance introduced by data augmentation. It does not incur any privacy cost because, again, like we are clipping at the right level our gradients, and so we are only just incurring the privacy cost of looking at one sample. And so this plot on the top, on the bottom right here, shows this that with augmentation multiplicity. So this is the number of times we augment any particular image within the mini batch. As this augmentation multiplicity number increases, we get better performance consistently. And then the final trick that we use in this paper is that we do parameter averaging, so using an exponential moving average of the parameters of the model, so that this reduces the oscillations of the trajectory of our model, and we observe that this improves convergence and gives us an additional boost of 1 to 2% in practice. And I'm now going to hand over to Soham for the rest of the presentation.
Thanks a lot, Leo. I'm just going to talk about now how we put all of these results together and then scale it up to really practical levels of performance for image classification using DP-SGD. So on this slide, I'm showing our best results on the task for CIFAR-10 classification, where we start training from scratch without using any extra data. So on the plot here, I'm plotting on the y-axis the test accuracy on the test set of CIFAR-10, and on the x-axis, I'm plotting the epsilon, which is the privacy budget. So the lower the epsilon, the more private the algorithm is. And I'm plotting our best results in blue. And sort of comparing it with all the other numbers that, all the other papers, numbers from other papers that have come before us. So as you can see that we get better results than all other papers before for any epsilon greater than equals to 3. And in particular, at like epsilon 8, which is the right-handmost point of the plot, epsilon 8 is kind of a standard benchmark that people have used in the community for differentially private training. We get quite a large boost over previous results. So like our best result, for example, at epsilon 8 gets up to 81.4% test accuracy. And these best results are obtained using a fairly deep model. This is a wide ResNet with 40 layers. And then we use this deep model and then scale up kind of the batch size we use, the augmentation multiplicity we use, and the amount of compute we use. And we get these really big boosts over prior performance. And it's worth noting that we kind of train significantly larger networks with DP than previous work. And a lot of it was enabled through kind of the tricks we use to improve signal propagation and convergence that Leo was talking about in the previous slides. And another thing I wanted to point out is that for very low epsilons, this paper by Kramer and Bonnet slightly outperforms us, as you can see on the left and two most points in the plot. While, so Kramer and Bonnet, this paper sort of uses handcrafted features and then learns a linear classifier on top. And while it's possible to get really good results at like small epsilons and fairly small problems, we really focused on kind of standard architectures that have been shown well to scale in non-private training, because we think that's the easiest way to scale it up to larger data sets and more challenging problems, scale DP up to more challenging problems. So if you go on the next slide here, we can see that we get similarly large improvements when we start training on ImageNet, which is a significantly harder problem than CIFAR-10 classification. So here we are doing ImageNet classification without using any extra data. And really, I think the only prior result we found in the literature was this paper by Kurakin and others using a ResNet 18, where they achieve a top one accuracy of 6.9%. And in contrast, we use normalizer-free ResNet, which removes the batch normalization, as Leo mentioned earlier, and using like a 50-layer version of the normalizer-free ResNet, we get a top one accuracy of 32.4%. So this is using the 50-layer normalizer-free ResNet and using all the other tricks that Leo mentioned before. So this is quite a large increase over previous results. But like 32.4% on ImageNet is still quite a low number, and like it's not really anywhere close to the point where practitioners would start getting excited and start wanting to use these kinds of techniques. And one of the main kind of limiting factors when scaling to kind of these large data sets like ImageNet when training from scratch is the amount of compute we need to be able to train these models. So next, we're going to talk about how we, in the next slide, we're going to talk about how we can leverage pre-training to reach practical levels of performance. But I just quickly wanted to stop here in case there are any questions before I move on to talking about pre-training.
Hello.
Hi.
Hello. Nice presentation. I have a question regarding to the amount of noise. So when the model contains millions of parameters, so adding differential privacy noise to the model is not realistic because it will consume a huge memory of GPU. So my question here is, can we only add differential privacy to a single layer instead of adding the noise to the whole model? Like we add differential privacy to a fully connected layer. And can this method guarantee the privacy?
As far as I'm aware, I think it's going to be very hard to attain differential privacy guarantees without adding noise to every parameter. That's the analysis that's this kind of standard analysis where everything works out nicely. It might be significantly harder to come up with kind of the same level of guarantees if you don't add noise to every parameter. I will say though, like that, we have scaled to models. I understand that doing these experiments on a single GPU is hard, but we have been able to scale to models significantly more than 1 million parameters. I think like these models that we are talking about have significantly more parameters. And like if you kind of can scale it up, things still work absolutely fine. And you can get very, very good performance.
And just to add on that, so one difficulty is not necessarily the compute requirement for a single update. Like adding noise to a large number of parameters is not necessarily a big issue. But what happens in practice is that in high dimension, this noise can become overwhelming. So it might be hard to learn without noise, even if you're able to add to that. And just another like minor comment. One way also of like adding noise to fewer parameters is if we freeze the others, right? Like we can decide to freeze a part of the model, and so like I think this is actually something is quite relevant for pre-training that Soham will talk about soon, where we do use like this sort of technique where we use like part of the model does not is kept frozen while we only fine tune some other parameters, which does preserve differential privacy.
Okay, thank you.
Hi, I have a quick question as well regarding the list of modifications you guys implemented. So I noticed you mentioned you try to investigate the improvement by adding them one by one. Did you investigate whether the order matters, especially for ones such as weight standardization and parameter averaging? Like the improvement is rather small, so maybe it'll be just eclipsed by a later improvement.
Yeah, I think so. For weight standardization, it works better for larger batch sizes. And there's some literature in kind of the non-private training which have similar kinds of observed similar kinds of phenomena where like it kind of the benefits start to become more apparent in the large batch case. For parameter averaging, I think we saw kind of the benefits pretty much uniformly across all batch sizes. Augmentation multiplicity, for example, I think starts to work better the larger the batch size, where like we start to we can leverage the benefits of data augmentation much better when the batch size is bigger. But we didn't do every permutation for the ordering. But yeah, roughly that's our intuition that like weight standardization and augmentation multiplicity, the benefits become more apparent in the large batch case.
I see. Oh, thank you.
All right. So I'm going to talk about now, move on to pre-training and show how we can leverage pre-training to kind of get really practical levels of performance. So first, I'm going to show some CIFAR-10 results. So here we're using wide resonance like before, but instead of starting training from scratch, we're going to pre-train non-privately using regular SGD on a downsampled version of ImageNet. And then we're going to fine-tune on CIFAR-10 using DP-SGD. So in this kind of setup, we are assuming that we have some kind of public data set, and in this case, this is going to be ImageNet 32 that we can train on non-privately, and then we fine-tune on the sensitive data set for which in this case, for our purpose, is CIFAR-10. And we want to see how well we can do on the CIFAR-10 task when under this setup. And we're going to look at both fine-tuning. When we're fine-tuning, we're going to explore both fine-tuning all layers simultaneously, or as Leo mentioned, like we're also going to explore fine-tuning only the last layer, where we freeze all of the layers, convolution layers, and then only fine tune the final classification layer for CFARTEN. So here are the results that we get. So the top two rows show previous work at different epsilons, and then I'm showing the results on fine-tuning just the classifier layer and when fine-tuning all the layers at different epsilons. And you can see that at all epsilons, pretty much at all epsilons, fine-tuning, we found that fine-tuning all the layers is better than fine-tuning just the last layer for this particular problem. And in particular, we get really impressive, I think, very high numbers where, like at epsilon 8, for example, we are over 96.5% training accuracy, which is kind of a standard performance that non-private training also gets to. So these results already indicate that you can get to very high performance when in this pre-training fine-tuning regime. And it's worth pointing out that since our paper came out, there's been this other paper, Wu et al. That I cite below here, which have also improved on our fine-tuning results on CFARTEN using a larger model. Next slide. Yeah. And we can extend these results in the pre-training scenario when we to like larger data sets like ImageNet. So in this, for our ImageNet experiments, we consider normalizer free resonance as before, which we pre-train non-privately on this data set called JFT 300 million. And then we fine-tune on ImageNet using DP-SGD. And for these experiments on this kind of, on this slide, we're comparing fine-tuning all layers versus fine-tuning just the last layer under a small compute budget. Next slide here. So here are our initial ImageNet experiment, ImageNet results. So on the left plot, I'm plotting the top one accuracy on the y-axis versus different models, different normalizer free resonance on the x-axis. So going from left to right, the model size increases, and we are comparing fine-tuning just the last layer versus fine-tuning all the layers in this scenario. So we see that, two things immediately pop out. One is that fine-tuning the last layer in this setting seems to be doing much better than fine-tuning all layers. And this, we hypothesize, could be due to a fairly small distribution shift between JFT and ImageNet. And more interestingly, perhaps, we see that as you move from the plot from left to right, we see the performance keeps improving. So that means that the better or the larger the pre-trained model, the better the downstream results on fine-tuning on ImageNet. And our best result on this plot, for example, using a normalizer-free ResNet 200, gets up to almost 80% top one accuracy. Next slide, Leo. So, in addition to the observation that a better pre-trained model leads to better downstream results, we also saw that using a larger or a better pre-training data set can also lead to better downstream results. So on this plot here, we're plotting top one accuracy again versus epsilon, different privacy budgets for our ResNet 200 model, the normalizer-free ResNet 200 model, where in one case we are pre-training on JFT 300 million, which is a data set of 300 million images. And in one case, we are pre-training on the data set JFT 4B, which contains 4 billion images. And we're roughly training each model for the same number of steps. So like it's not the differences in performance is not really accountable to more or less amount of pre-training, but rather we're trying to understand the effect of the quality of the pre-training data set. And you see that pre-training on JFT4B, for example, consistently outperforms pre-training on JFT 300 million across all the privacy budgets that we considered. So these numbers are with a slightly larger batch size, 2 to the 18, and then we also scale up the compute. and use our largest NF-ResNet model, 200-layer NF-ResNet model. And there we see consistently like this observation that better pre-trained using a better pre-training data set can lead to better fine-tuning results. And our best result in this for these experiments at epsilon 8, for example, gets up to 82.2% top-one accuracy. Next slide, Leo. So, using these observations, we scaled up both the model size as well as the dataset size to see how well, what's the best kind of performance we can achieve with under the setup. So we consider like this normalizer-free networks, the F3 version of this normalizer-free networks, which is like this family of image classification models without batch normalization, which we pre-train on JFT4B. And so here are our best results on ImageNet, where we are plotting performance from epsilon 0.1 to epsilon 8. And we see that, at epsilon 8, we get a top-one accuracy of 86.7%, which is, pretty much like, only a 2% gap between the non-private performance that this model achieves on ImageNet. And perhaps even more kind of surprisingly, we get really strong performance at really low epsilon budgets. For example, at epsilon 0.5, we get up to almost 84% top-one accuracy, which is higher, as Leo mentioned, than many kind of deployed models of image classification, non-privately deployed models of image classification. Next slide, please. So, we are getting these really impressive numbers on ImageNet, but as I mentioned, like there was always this question whether there was a very small distribution shift between JFT and ImageNet. So we considered another fine-tuning task where instead of fine-tuning on ImageNet, we're fine-tuning on places, where this is like a scene recognition data set. And we wanted to see if like, all of our insights sort of carry over to when we have a larger distribution shift between the pre-training data set and the fine-tuning data set. And we see that that is still true. Like here, for example, I'm plotting performance using a normalizer-free ResNet 50 at epsilon 8, and tuned also like our best performance with this model when we fine-tune it non-privately. And we see that, first of all, we see that fine-tuning all layers in this case is better than fine-tuning only the last final layer. And more interestingly, we see that the performance between the non-privately trained model and the privately trained model at epsilon 8 is again very, very small. It's only a 2% gap between the two models. And so even in this scenario, we can reach, close to the performance of the non-private training when in this pre-training fine-tuning regime. All right, so that was our results with pre-training. I'm just going to quickly stop here for any other questions before I move on to the last section. All right. So as Leo had kind of alluded to earlier, hyperparameter tuning is really important, and getting it right is really important for DP-SGD. And because of the way that you add noise and there's a limit on the number of training iterations under a pre-specified privacy budget, the regular settings that the practitioners have been using for hyperparameters in non-private training don't necessarily carry over to private training. So we did a small kind of study of how the different hyperparameters of DP-SGD interact with each other when training on these kinds of problems. So here we are gonna look at, so for this small study, we're just going to look at CIFAR-10 classification training from scratch. So the first question we wanted to explore was that whether whether there's an optimal noise scale when training with DP-SGD. Like you can ask whether there's an optimal noise scale or whether it's always better to kind of increase the amount of noise you add, which enables you to train for longer and longer under a fixed privacy budget. And you see that, so in this plot here, I'm showing the accuracy versus the noise parameter. So every point on this plot has been independently tuned for the best learning rate. And this is at a fixed batch size. So we see that there's very clearly a peak there's like a very clear peak of the noise of performance at a particular noise parameter, which means that there's an optimal noise scale given a fixed batch size. Next slide. And so because the optimal noise scale corresponds to how long you train your model for, this means that there's an optimal compute budget for all of your training runs with DP-SGD at a fixed batch size. So for example, in the middle plot here, I'm just plotting the same plot on the left as on the left, but on the x-axis, I'm just translating the noise parameter to correspond to the corresponding training iteration budget T. And you see, there's an optimal training iteration budget. And you might think that this might be due to overfitting or something like that. So like we also show on the right here, performance on the training accuracy versus the training iteration budget, and you see the same kind of peak at the same point of training iteration budget of 2,500 steps. So this is actually quite different from non-private training because when doing non-private training with, let's say, regular SGD, training for longer is always usually better on the training set. And usually, do early stopping just so you don't overfit on the training set and get the optimal performance on the validation set. But in DP-SGD is very different in the sense that there is there's an optimal compute budget even on the training set, and correspondingly on the validation set. Next slide. And you can ask, like, because we are talking about increasing the batch size, how this optimal compute budget scales or changes with the batch size. And we see that, this optimal compute budget has kind of two different regimes depending on the batch size. So on the plot on the left, I'm plotting the optimal iteration budget for different batch sizes on the x-axis. And you see that, so each of these points might tuned independently again. And you see that for a small batch size, the optimal number of iterations keep decreasing and then becomes constant after a particular threshold. In the middle plot, I'm plotting the corresponding optimal number of epochs, which correspond to the left plot here. And you see, for example, that for any batch size less than 2 to the 11, the number of epochs that is optimal to train for is roughly constant, and then it starts increasing after a point. So, you can say that, like, and on the right plot, I'm showing the same plot that Leo showed earlier, which corresponds to these experiments of how performance keeps increasing as you increase the batch size. So, kind of the main takeaway from these plots is that DP training is compute efficient up to a particular batch size, in which in this case it's up to 2 to the 11. But after that, it keeps requiring more and more compute as you keep increasing the batch size to get optimal performance with the batch size. And if you go on to the next slide, Leo, we see that, like, this batch size threshold after which DP-SGD training starts becoming compute inefficient is determined by when the optimal learning rate becomes constant. So here on the right plot, I'm showing the optimal learning rate that we got for each of these experiments. So on the x-axis is still this, the batch size grid, and on the y-axis is the optimal learning rate. And you see that you achieve on the left side of the plot, the optimal learning rate keeps increasing linearly with the batch size, and you start becoming kind of compute inefficient when you reach this batch size threshold of 2 to the 11, after which the optimal learning rate becomes constant. All right, so next slide here. So just to wrap up, so in a nutshell, what we show is that standard computer vision models can work surprisingly well with DP-SGD. When you combine it with tricks that improves its convergence and trainability, with careful hyperparameter tuning, and when you use enough compute to be able to leverage all of these tricks properly. And then when you add in pre-training, on some kind of public data set combined with standard models, we can reach practical levels of performance with DP-SGD, which can reach very close to non-private performance. And on the next slide, Theo, I just want to end on a note of caution, I guess, is that you might ask whether these results are enough for practical use of DP-SGD. And while these results are very promising, at least for image classification, there's several important considerations to think about when you actually want to deploy a model. Like you might want to think about at what level you want to guarantee privacy, whether it's at the user level or at the item level or record level. Choosing epsilon is a non-trivial issue, as Leo mentioned. I think it's also important to do very careful evaluation to kind of avoid disparate impact on underrepresented groups. All of the experiments in this paper, we are kind of considering idealized academic data sets, I think, where all the classes have similar number of images. So that's an important issue to think about. And also, when you want to deploy these models and want to use pre-training, you need to also think about the sensitivity of the pre-training data set. And with that, I think that's all we have. I just want to point out that we have code available at this link here. That's available. So this is code in JAX, and we're happy to take your questions.
All right, so very nice presentation, also very interesting work. So are there any questions?
Hey, Soham and Leo, it was a great presentation. Hi. I had a quick question. So we were seeing that when working with pre-training models, sometimes fine-tuning all layers versus sometimes fine-tuning just the last layer or individual layers work better. So do you have some kind of intuition on what might be causing this difference? Like, is it data set dependent or is it more model centric?
I think, I think we don't have a very precise answer for that. I mean, we have a rough intuition that when there's a larger distribution shift between the two, the pre-training and the fine-tuning data sets, fine-tuning all layers is better versus fine-tuning just the final classification layer. But I think it's hard to quantify kind of distribution shift. So we haven't really done those experiments yet in much detail.
Yeah, at the risk of being even more vague, it's a bit like the difficulty of the learning task that dictates in if the task is extremely easy from a learning point of view, then just learning the last classifier layer will be enough. But when you want to learn more, the recording has stopped. When you want to learn more complicated things, then learning all layers actually can work better.